When choosing a degree, many of us have likely researched the potential salaries. In doing so, we might have stumbled upon a degree called computer science and thought, wow, I'm all in for that juicy 100k. But before you rush into gathering your documents to apply for a computer science degree, let me give you a brief overview before your days of no glasses, social isolation, and back problems are about to come. Okay, I'm just joking. Or maybe not? Anyways, let's just start. The computer science degree can be summarized in 4 main fields: mathematics, computer engineering, applied computer science, and theoretical computer science. Alright, let's start with math. I know some people love it and some people hate it, but math is a very important aspect of computer science. So what do we actually learn in these math classes, you might ask? So we are starting with calculus. In calculus we are going to learn about functions, understand their behavior, and their specific characteristics. For instance, we will analyze the maximum or minimum values of a function or calculate the area under it. Furthermore, we will learn how to approximate certain functions to simplify their analysis within a specific domain. In the linear algebra part, we're going to learn about vectors and matrices and how to solve linear equations using matrix notation. A vector can be thought as of an arrow in a dimension, while a matrix, well, it's kind of like a wonder machine. If you put data into your matrix in a certain way, you can do nice little things like this happy dancing little skeleton figure who just finished his bachelor degree in computer science with the cost of his hair and skin and flesh. Okay, not funny. Alright, poor young man, but cool animation, huh? Then let's go to the not so cool part, discrete math. Actually, this is not that bad. So the first thing you're gonna learn is set theory. A set is basically just a box of things. Everything what you want to put in the set is part of the set, but duplicates are not allowed. But in the beginning we only talk about numbers who are in a set. Then you learn about the different proof techniques in mathematics, including direct proof, proof by contradiction, proof by contraposition, and mathematical induction. If you've never done a mathematical proof, this might sound easy, but believe me, as soon as you get your first assignment and try to do these proofs, you're gonna miss your high school days of math. Another part of this course will be number theory, where we primarily discuss prime numbers. You're gonna learn why prime numbers are going to safeguard your biggest secret that you told your friend over WhatsApp when you were drunk as hell on a party. So, the short explanation is that we multiply two large prime numbers p and q together. It's easy to do that, but trying to do the reverse is much harder. After a bit more magical mathematics, our secrets are then safe. Thank you, Mr. Prime Number, for keeping our secrets safe. The last topic we learn about in discrete math is also one of the most important topics for computer science, no matter for applied computer science or theoretical computer science. It's called graph theory. Graphs again? Well, these graphs are different from the graphs we learned about in calculus. The graphs you learn about in this course aren't dependent on the x-axis and y-axis. They are often made of lines or arrows connecting circles, where the lines indicate that the circles are connected to one another. Sometimes there are numbers on the arrows and lines, which can be interpreted as distance between the connected elements, but later more. Okay, we are finally done with the math part. Let's follow up with the computer engineering part. The first course is going to be about computer architecture. We will start by learning that the computer only understands 1 and 0. You can imagine it like this. If you press a switch, the light source will turn on. If you press it again, it will turn off. So basically power on, power off. Nice. Now you know the binary language. The next step will be logic gates. Logic gates are based on Boolean algebra, and the most fundamental ones are AND, OR, and NOT gates. So what are these logic gates doing now? Well, they essentially bring logic to our computer. For example, you can now connect multiple switches to our gate and then connect it to our light source. The light source will only light up if the switches are turned on according to the rule of our logic gate. For instance, consider our AND gate. If only one switch is turned on, the light source will not turn on, because according to our rule, it will only turn on when we press both switches. Okay, now if we use these logic gates and connect them in a smart way, we can do calculations that look something like this. Another cool thing is, we can also build memory by connecting the basic gates like this. Okay, we did so much theory now. The programming should slowly start, right? Wait. Guys, what are you doing here? I said we should slowly start to code, but not with you guys. We're starting with him. So, what is assembly actually? Well, let me explain. We already know that computers only understand zeros and ones, which is also called machine code. What programming languages normally do is use a compiler to translate the code into machine code. But before this step happens, the code typically gets translated into assembly code and then into machine code. So why are we writing assembly code then? When we write assembly code, we have direct access to our memory, and we can perform very fast calculations by loading our information into our CPU registers. For the people who want to see how a block of code in assembly versus how a block of code in normal programming languages looks like, here's a picture. Okay, enough of computer architecture. Let's switch to the computer network course. So what is a network? A network is a collection of interconnected devices that communicate with each other, send and receive data from each other. With that in mind, we can now try to understand how our internet works. So basically, we are all just connected with cables around the globe, and your internet service provider gives you access to this entire cable network. With that being said, your provider also provides you with an IP address that helps you to be identified in the whole network, so people know where to send data to you. But now the question arises, what happens if we have multiple people in our Wi-Fi connection network? Couldn't it be that my WhatsApp messages that my friends send me goes to my mom's phone instead of mine, if we only have one single IP address? Luckily no, because every device in the network gets a unique IP address as well, so there can be no confusion or secrets exposed that nobody should know. Now, after all this computer engineering, we finally go to the long-awaited applied computer science. So the first course in this section will be Introduction to Programming. And now you guys can finally make your entry. With these programming languages, we can finally write code that's more easier to read and work with than assembly. The first thing we're going to learn about is data types, which essentially are just ways to store data. An integer can store only whole numbers, floats can only store decimal numbers, chars can only store single letters, and lastly a boolean can only store a true or false value. Alright, now let's talk about different ways to store chunks of data. Imagine you want to have a whole block of integers. You can achieve this by using a data structure called an array. An array has a fixed size, meaning that once you've initialized it and your program is running, you can't change the size anymore. So adding more elements will not work. But before we solve this problem, let's look at how everything looks in our memory. For simplicity reasons, we say that every data type has the same size. As we can see, data types can be placed anywhere, but arrays take a whole section of blocks, and every block that belongs to the section is in a fixed order. Alright, what is the exact problem with changing the size of our array? Well, we cannot change the size of the array because we could override our values in our system that doesn't belong to our program. So what's the solution? The solution is called a linked list, where you essentially have two blocks of memory. You store the data in one block, and in another block you have a so-called pointer, which points to another linked list element, thereby building a data structure that can be resized. With a linked list we can also build this binary tree, and if we put data in the right order, meaning smaller elements on the left and bigger elements on the right, we can access our data fast because we have a sorted system in our structure that guarantees us not to go through every single element in the binary tree and still finding the right data. Speaking of the right order, sorting arrays and lists is also very important. That's why you will encounter many sorting algorithms in this course. Here's a list of algorithms you will probably learn. Alright, after coding all these things, we also need to evaluate how good our code is by figuring out how fast our code is running. We figure it out by looking at the structure of the code and thinking of the worst possible scenario that can happen. After that, we analyze the code and figure out how many times the lines in the code get executed in the worst case. We're going to make the size dependent on the input of the code, which we call n. And depending on n, how often the code gets executed, we're going to use these notations: O of n log n, O of n to the power of a, and O of 2 to the power of n. This so-called big O notation helps us to give a rough estimation and not to worry about the exact numbers of how many lines really got executed. Look at these examples. As we can see, you only care about the biggest term and not about the constants. Then let's look at two programming techniques. Let's start with recursion. Recursion is basically a function calling itself, but you need to put a condition where the function stops calling itself. If you don't do that, your code will crash. If your code could crash because of recursion, what's the point of doing it? Well, sometimes recursion can help us to write only a couple lines of code to solve a very hard problem. And if you wouldn't use it, your code will be way longer and way more complicated. The second programming technique is called divide and conquer, which always is based on 3 steps. First step, you need to divide the subproblem into parts until you can solve the subproblems, meaning you now conquered the problem. In the end, since you've divided so far that you can solve every subproblem, you put them back together and construct a solution as a whole. Why are we doing this? Well, divide and conquer can help us to solve problems faster. If we look back at our list of sorting algorithms and add the O notations to every algorithm, we see merge sort has the best running time out of all these sorting algorithms, and this is all thanks to divide and conquer. Alright, let's talk about object-oriented programming, or short OOP. Many people struggle with understanding classes, but classes are essentially just blueprints where you write down what traits this class should have and what they can do. The traits you call attributes, and what the class can do is called methods. Let's look at this robot class. He has length, height, and battery status as attributes. And his methods are pick up and pick down. Congrats, you now have to understand what object-oriented programming is. Okay, since all the students love data structures so much, they will let you attend data structures and algorithms directly after introduction to programming. In the data structure part, you're gonna learn about stacks, queues, dequeues, and so on. These are very easy to understand, so here the short form explanation. You can put stuff on top of the stack and only take the top element out of the stack. A queue works like a real-life queue. The first element, or the first person who went into the queue, will be the first person to be out. And a dequeue works like this. You can add and remove from both sides. Alright, let's finally talk about graphs more in depth and how to explore them. You see the one on the left is called BFS, breadth first search, and the one on the right is called DFS, depth first search. From these short animations we can see how they operate. We saw BFS explores the breadth and DFS explores the depth. BFS uses data structure called queue to achieve this behavior, and DFS uses a stack. Okay, these algorithms explore the whole graph, but if we change the algorithm a bit, we can also turn it to find us the way from A to C instead of just exploring the whole graph. Alright, let's just say we want to have the shortest path. These two algorithms we talked about can't achieve it. We would only get a path from A to C, but not the shortest path. That's why we have another algorithm that would do the job for us. It's called the Dijkstra algorithm. But before that, we need to add numbers to our edges that represent the distance between the nodes, so we can use this new algorithm. But Dijkstra's algorithm is still problematic because it's going through every node in the graph and calculating the shortest path for every node. You might ask, isn't that good? Well, not really. Imagine you're asking Google Maps the shortest path from your home to your campus. Dijkstra would now search the whole world and tell you the shortest path from your home to all locations, even though you just want to know the shortest path to your campus. How can we optimize this so we don't have to explore the whole world? Luckily, we also have an algorithm called A*. It's basically Dijkstra, but it helps you to find the path with a direction. This direction is provided by a so-called heuristic. But with the heuristic, you don't necessarily get the shortest path anymore. But most of the time, if you don't get the shortest path, it's already a very optimized one. And that's still better than waiting till you're unalive because you're still waiting for the shortest path with Dijkstra. And now to the last topic in this course. It's called hashing. Hashing is basically you have a key and a value. You call this an entry. The key is the one who's gonna get hashed. And through our magical hash function, our entry will get added to our hash table. If we now want to access an element in our hash table, we do that through a key, and our average access time will be O of 1. But if we're gonna choose a very bad hash function, our magical effect will be weak, and we will have a negative effect on our average time complexity. Okay, now to the last part, theoretical computer science. The first course you're gonna attend is Formal Languages and Automata Theory, where we start with understanding what a language is. But before we do this, Let us first define some things. An alphabet is with what kind of symbols we can build words. Speaking of words, let's do an example. Let's say we have an alphabet with the set of A and B. Then we can build words like this or this. Same principle with 0 and 1, but you can define your alphabet with whatever symbols you want. For example, you could do silly symbols like this as well. Then there's also the star symbol that you can put above the alphabet set, and what this essentially does is that we now contain every possible combination with the symbols of our alphabet. Alright, now what is a language? A language is basically just a set of words where the words who are in the language got filtered out by a condition. For example, now our language L equals to all the words over the alphabet A and B, where every word that belongs to our language ends with an B. And that's basically a language. Now let's go over to automata. An automaton is just a graph with circles, which represents the states, and the arrows with a symbol from the alphabet represents the transition to another state. A double circle means it's the end state. The connection between automata and formal languages is simple. Automata help you to visualize your language and see if a given word is in your language or not. Let's take our language from before and draw the automaton for it. Now let's take the word AAB and see if our automaton accepts it. Surprise, surprise, it does. Okay, it's a very simple computation model and very limited. We couldn't compute anything with it because we are lacking memory with this model. That's why we're going to the next and last course. Then let's start with computability and complexity. In the course before, we stopped at automata and we realized we still lack things. But in this course, we're gonna learn about computation model that is called the Turing machine, which is like the automata we know, but it has a few additional things, like an endless long tape, what will be our memory, and on the transitions, on the arrows, they're also different now. With all these additional things, the Turing machine is the most powerful computation model we know, but we are not going to do everything on Turing machines, because that would be too much brain gymnastics. Instead, we can also use programming languages / pseudocode, because everything what we can compute with our programming languages, a Turing machine can also do. Okay, great, let's go. We finally reached the state of a programming language. We can now go and solve any problem, right? No, this course will also teach you limits that you cannot solve any problem. Most famous example is the halting problem. The problem basically says, given some program and input from this program, we're trying to write a magical program checker that can determine for every program and input you give whether the program will eventually terminate or not. But this is proven that this magical program checker does not exist, no matter smart our programming gets or not. We also call this problem undecidable because we can't get an output for every input we give. So now we know that we can't solve all the problems. Let's go over to the complexity part, where we only look at problems we can solve / can decide. Alright, what are we trying to analyze? People who are familiar with coding already know that you can write fast code or you can write slow code. In the applied computer science part, we already talked about the big O notations, and in this course we're going to look at two complexity classes, P and NP. The class P contains all the problems that can be solved in polynomial time, and NP is the class that contains all the problems who can be solved in non-deterministic polynomial time. But well, this statement might not be that correct, because this assumption that I'm doing is that P is a subset of NP. But to this day, nobody proved that P is a subset of NP, nor did anybody prove that these sets might be equal. But the possibility is still there. What is the problem now with these NP problems? Well, there are so-called NP-complete problems, and nobody found a solution in polynomial time for them. And problems that don't run in polynomial time will take a very long time to compute. So long that when you wait for the result, you might be already unalive. But as mentioned, the worst thing is that nobody has proven yet that these problems might be in P or not. So if you still have any spare time while studying computer science, maybe you are the genius who is cracking this mystery. But why should you try, you might ask? Well, this problem belongs to one of the 7 millennium problems. For each problem solved, you get $1 million US. So why not give it a try? maybe you're the guy who made it, and drive with his Ferrari to the campus. How could you prove it? If you would try to prove P equals NP, you just need to take an NP complete problem and reduce it in polynomial time on the problem in P. Meaning, change the input of the NP complete problem so it fits the problem in P. But this change needs to happen in polynomial time. However, to this day, this problem will still remain a mystery. Alright guys, thanks for watching. If you enjoyed the video, you can leave a like and subscribe, as I will be creating content on this channel in the future that explains some of the concepts mentioned in this video. See ya.